everybody, this is Dr. Bricker here with a review for Exam 1. So the exam will be, it'll look a lot like the practice test that you have. There'll be 12 questions, multiple choice, but you have to show your work. If you show no work, you get 0 points, so you have to show your work. You can get partial credit that way. I also recommend making your own formula sheet. So sort of like maybe a page or so with formulas, notes, example problems, whatever you want to put on there. That'll help you do the test. And it is over chapters 1 through 5. So motion, two-dimensional motion, and Newton's laws. To study for it, I would definitely go over the practice test, which hopefully you have and you're watching this video. I would also review the first 4 homeworks, homework 1 through 4. Go over the PowerPoints if you have a chance, reread the chapters. If you don't have a chance to go through all of the chapters, the end of the chapters have nice little summaries at the end. Okay, so I will go over the test in just a minute. Just keep all this stuff in mind about the test, okay? Okay, so let's just start with the test and I'll give you some hints along the way. So as you see, it says show all work for credit. No work, no credit. Okay. So the first one, a car is moving with a speed of 32 meters per second. The driver sees an accident ahead and slams on the brake, causing the car to slow down with uniform acceleration 3.5 meters per second squared. How far does the car travel after the driver puts on the brakes until it comes to a stop? Okay, so let's see. Initial speed, 32 meters per second. Final speed would be 0 when it actually comes to a stop. Now this acceleration means we're slowing down, so minus 3.5 meters per second squared, similar to a problem in the chapter actually. And how far does the car travel? Okay, so right now this question's worth 10 points. I would give you, just for writing this stuff down, 2 points. So you get about 2 points for kind of organizing your thoughts. Okay, so this is a kinematics problem. We want to know how far we travel. So think back to the kinematics equations that you have. Now there are 2 of them that involve distance traveled, displacement I should say. Final velocity squared is equal to initial velocity squared plus 2a delta x. Okay, let's see if this one will work. Final speed 0, we know the initial speed, we know the acceleration. This formula will actually work for you. So at this point, by identifying the correct formula, I would probably give you 5 or 6 points out of 10. Probably closer to 6 actually. So then let's actually solve it. Final speed of 0, subtract this from both sides, divided by 2a, that will give you delta x. So probably now you're up to like 7 or 8 points. And then we have to actually do this. Minus 32 meters per second squared divided by 2 times negative 3.5 meters per second squared. That will be delta x. Okay, so I'll leave it to you to work it out. That's the way to do it though. Okay, so after you have the correct answer over here in meters, now you have 10 out of 10. So if you miss a negative sign and it's not a consequential negative sign, you might only miss a point or 2. Or if you do some of the algebra wrong, maybe a few points off there. But it's organizing your thoughts, coming up with the correct concept, and then doing the actual work. Okay, good. Next one, an object of mass 10 kilograms. Let's see, pulled on a horizontal surface by a horizontal force of 50 newtons to the right. So why don't I just call this tension? Again, you can call this stuff whatever you want to. The object is accelerating at 1 meters per second squared. What is the frictional force? Okay, so a free body diagram would be helpful for this one. Normal force, weight, what I call the tension here, frictional force back the other way. And I drew tension larger than friction on purpose because the acceleration is this way. Okay, and then I could use Newton's second law. Net force is equal to ma. Okay, there's my little box. Tension minus frictional force. So do a little bit of algebra. Frictional force then turns out to be, moving this to the left side, ma to the right side, T minus ma. Okay, so then I would have 50 newtons minus 10 kilograms times 1 meter per second squared. Okay, that's nice. Turns out to be 40 newtons. That's how much friction must be. And then it's always a good feeling to see the answer there. So if you did none of this, you circled the answer, you get 0 points. Put as much work into it as you can. You know, if there's only like one line of work, but you have the right answer, you're still not going to get the full points. You have to show, you know, at least most of the work for full credit. Okay, and technically it says show all work for credit. Okay, very good. So I'll put this off to the side. You know, make sure that you keep this close by, because you're going to have to somehow make a copy of it and get it back to me. I'm making a separate video talking about a couple of hints for that. Okay, which of the following graphs represents an object with zero acceleration? Okay, so zero acceleration means the velocity is constant. Okay, let's see if there's any constant velocity ones here. Well, B is constant velocity, right? The velocity is not changing. This graph of position versus time, though, this is also V constant. So the choice here would be graphs A and B. Let's see if C it's changing, D also, the velocity is also changing. So the correct choice would be graph A and B. Okay, and again, even this kind of problem you can get partial credit. Now as far as explain goes, you could do this with equations, you could do it with words, a combination of those. I would just say zero acceleration means constant velocity. In B, velocity is not changing. Velocity not changing. And choice A means constant velocity. Something like that. Okay. All right, let's take a look at the next one then. A car starts from rest. Okay, so it starts from rest. Initial velocity is 0. And accelerates uniformly 4 meters per second squared for 5 seconds. It then maintains the velocity it's reached for 10 seconds. Okay, so however you want to organize this, I'm going to just say, I'll just call this like V1. And the time here is for 5 seconds. So we're going to have to distinguish this. Maybe this could be like T1 then, since I'm calling this one T2. Actually, it was 10 seconds, not 5. So whatever velocity we reach here, you start with at rest, accelerate for 5 seconds, you reach some V1. Now you keep that V1 for 10 seconds. Then you slow down at a steady rate for 4 seconds. Okay, so why don't I call this acceleration 3 or something? So minus 2 meters per second squared because we're slowing down. And I'll call this one T3 for 4 seconds. What's the final speed of the cart? Okay, so this is a little trickier than the other kinematics problem that we did. You start from rest, accelerate for 5 seconds at this rate, getting up to V1. You keep that V1 for 10 seconds, and then you slow down for at this rate for 4 seconds. All right, well, let's figure out what V1 would be. So a later velocity is equal to the earlier velocity plus A times T. That's just the first segment that we have. So 0 plus 4 meters per second squared for 5 seconds. This would get us up to 20 meters per second. And then we keep that for this middle segment here. Okay, and then we slow down at this rate. So what's the final speed? Why don't I call this V3 then? What do we slow down to? So again, later velocity would be earlier velocity. So later, that's what I'm looking for. Earlier, well, this is the earlier one, plus AT, A3, T3. And again, you can call them whatever you want to. Okay, so then this would be, we're going from 20 meters per second, and then we're slowing down, so plus negative 2 meters per second squared for 4 seconds, 12 meters per second. Good. Again, it's always a good feeling to see the correct answer there. So if you run into a problem and you don't really like that problem, skip it and then come back to it. This one wasn't so bad, but if you run into one like that. Okay. So if you pound a feather with a hammer, which one feels the greater force? So you take a feather and hit it with a hammer. Which one feels a greater force, the hammer or the feather? Well, it turns out the size of the force is exactly the same. So this is by Newton's third law. For every action, that means force, there is an equal and opposite reaction. So therefore, the forces are the same. Forces are the same. Oops, there we go. Okay, so you'll see a Newton's third law one. It's the same idea. The book has an example of you're driving down the road in your truck and a mosquito gets hit by the truck. So the force on the mosquito from the truck is the same thing as the force on the truck from the mosquito. Well, how could that be? It can be because it's the same force, but the same force applied to a big object like a truck, the truck doesn't care. That same force applied to the mosquito definitely feels that. Okay, good. So you'll see a Newton's third law one, similar to that. Again, there's no formula. It's basically this idea. Okay, next one. This is from chapter 5. The coefficient of static and kinetic friction on a 3 kilogram box. Okay, mass is 3 kilograms. Coefficient of static friction is 0.4. Coefficient of kinetic friction, 0.3. Static friction is always greater than kinetic friction. What is the force of friction on the box when a 15 Newton horizontal push is applied to the box? Okay, so with these problems, let me draw the free body diagram. Normal force, mg, this is 15 newtons. We want to know how much friction is. We don't even know if it's static friction or kinetic friction right now. Let's see how much the maximum amount of static friction is. So maximum static friction is the normal force times mu sub s. That's the maximum amount. The normal force in this problem is equal to mg. Okay, so the mass was 3 kilograms, 9.8, and then 0.4. Okay, let me find my calculator. Okay, here it is. 3 times 9.8 times 0.4. 11.76. That's the maximum amount of static friction. So we are above that. This applied force is 15 newtons. We're above this, so we're not even in static friction. We've overcome static friction. So we'll have to figure out how much kinetic friction is. It's the normal times mu sub k. And again, the normal force is equal to mg. And I can put all this stuff in. 3 kilograms, 9.8 meters per second squared, and then times 0.3. Okay, so we've got 3 times 9.8 times 0.3. 8.82. So about 8.8. There we go. Good. So the first thing to do is to check to see if you're above static friction. We are. Our applied force is bigger than static friction, so we know it's kinetic friction. Now what if this applied force was only, say, 6 newtons? Well, if the applied force is 6 newtons, we haven't overcome the maximum amount of static friction, so the frictional force will only be 6 newtons. The frictional force is only, the static frictional force is only as large as it needs to be. So if you push with 6, static friction will oppose you with 6. Push with 10, static friction will oppose you with 10, until you get up to and over 11.76. Then you overcome static friction and you're in the kinetic friction regime. So the first thing to do with this, these kind of problems, have you overcome static friction? Yes. Then figure out how much kinetic friction is. If the answer is no, you have not overcome static friction, then the frictional force is equal to the applied force because it's not moving. That's what static friction means, it's not moving. Okay, so we're about halfway done, not too bad. A bucket is being lowered by a very light rope. The bucket is accelerating downward. Okay, so it's a bucket, tension, weight. Right, the acceleration is down, so the weight force has to be bigger than the tension. It doesn't mean it's in free fall. You're still holding it, it's just accelerating down. So this is a picture of what's going on at some point. The bucket's being lowered, it's accelerating down. For that to be possible, the weight has to be bigger than the tension. And okay, so the tension in the rope must be, so the tension must be less than the weight. And then the free body diagram is enough to explain it actually, but if you want to do a sentence or two, you could say, because acceleration is down, acceleration is down, the net force is down. Therefore, weight must be bigger than tension. Something like that. Okay, good. So you'll see a bucket one. I'm not saying it's accelerating down. Maybe it's accelerating up. Maybe it's going at a constant speed. Just be aware of this type of problem. Okay, let's look at the next one. This is a actually free fall problem. Human reaction time is usually greater than 0.1 seconds. So if your friend holds a ruler between your fingers and releases it without warning, how far can you expect the ruler to fall before you catch it? Okay, so somebody's holding a ruler between your hands, they let it go, the ruler accelerates down. How far is it going to go before you catch it? It doesn't look like we have a lot of information, but the initial speed is going to be 0, right? Because you're just going to drop it. The acceleration in the y direction also, you know that, negative 9.8. So really, you want to know how much is the displacement in the y direction. Really, we don't specifically want the displacement. We want the magnitude of the displacement. How far does it actually fall? Okay, so think back to your kinematics equations. This one pops into my mind. I'll put a little y there just to really emphasize it. So delta y, initial velocity times time, plus 1/2 at squared. Okay? And the acceleration in the y here, that's free fall, negative 9.8. It's not attached to a rope or anything, you just drop it. Okay, so if you start from rest, this one isn't too bad. 1/2, negative 9.8, and then t squared, 0.1 squared. Okay, so it's 4.9, 0.49, 0.049. Right, half of 9.8 is 4.9, and then multiply it by 0.1, and multiply it by 0.1 again, just to verify. 0.5 times 9.8 times 0.1 squared, 0.049 meters. Okay, and the answers actually here are in centimeters, so this would be minus, move it over 2 spots, boom, boom, 4.9 centimeters. That's the displacement. We just want the magnitude of the displacement, so we want this choice here. Okay, good. So definitely look back at the free fall problems that we did, like things falling from a building. I think we did something like that. Still just one-dimensional motion. Okay, so the next one here, a boy kicks a football from ground level with an initial speed of 20 meters per second at an angle of 30 degrees above the horizontal. what is the horizontal distance to the point where the ball hits the ground? So it's one of these. We did some problems like this. This is from chapter 3. You know the overall speed and you know the angle. So really they're asking what is the range here. Lots of ways of doing this. Probably the quickest way is to use the range equation. Divided by g. So that should ring a bell. This is we have everything. It's kind of a plug and chug problem at this point. You know the initial speed, you know the angle, you know g, you can figure out the distance. Okay? This is one sort of projectile motion problem. I'm not saying it's going to be a range equation problem on the test. Let me give you all the information for projectile motion. So this is motion in both the x and y direction. So in the x direction, I'll make a little table here. The acceleration in the x is 0, and the only thing that you have is the x velocity is the displacement divided by the time. In the y direction, you have all the kinematics equations. So you have final velocity in the y is equal to the initial velocity in the y plus acceleration in the y times time. Velocity final squared in the y is equal to the initial velocity squared in the y plus 2 acceleration in the y delta y. And then finally, delta y, initial velocity in the y times time plus 1/2 acceleration in the y t squared. And then if you have a picture like this, if this is the overall velocity and this is theta, this can be broken into its components, x and y part. So the initial velocity in the y is the overall velocity times the sine of theta. And the x velocity, which doesn't change, is the overall velocity times the cosine of theta. Okay, so again, I'm not saying it's going to be this exact situation where it's a projectile. You could use the range equation. So look back, I believe it's homework 2, where we had questions from chapter 3. If you remember, we had a question like you shoot a dart horizontally and it reaches some, you shoot a dart horizontally, it does this. And how far does it fall? We also had in the chapter a dog running off the end of a pier, using the x and y directions simultaneously. The thing that ties x and y motion together is the time. So sometimes you have to use the y information to figure out the time and then go back to the x position. I just put this problem on to introduce the topic of projectile motion. You'll definitely see one, and again, I don't know if it'll be this kind or if it'll be, take a look back at homework 2, something like that. Okay, good. So this is a good place to start. One other thing to mention is at the highest point, you could use this fact. The y velocity at the highest point is 0. Sometimes that'll help you, figure out how long it takes to get to the highest point, because the y velocity here is 0. Then the total time would be twice as much, or maybe you want to figure out what this highest point is. You could use that fact as well. Okay, so take a look back at the homework and the chapter on that one. Okay, so let's see. A girl throws a rock horizontally with a velocity of 10 meters per second. It falls 20 meters to the water. How far does the rock travel horizontally? Okay, so something like this maybe. So you throw it horizontally, it's going to do something like that. We want to know what's this distance. Okay, so we had a good little reminder, refresher in the previous problem. Velocity in the x, because it's thrown horizontally, it says it's 10 meters per second. It falls 20 meters. This distance here is 20 meters. So really, the displacement in the y is negative 20 meters because you've gone, it's gone this way. Okay, and then we want to figure out how much is this. Okay, so we also know the initial velocity in the y is 0, and we know the acceleration in the y is negative 9.8. Okay, so we have the x velocity. We're trying to figure out the displacement. If we knew the time, we could get the x displacement from this, right? X velocity times time is the x displacement. So if you knew the time, you could figure out how far over you go. Luckily, we can figure out the time from the y information here. Okay? So probably the one that comes to mind, there's two equations that have time involved. Remember this one. The problem with using this one, we can't get the time because we don't know the y velocity right before we hit the ground. So this one will not work for us. This one will, though. Okay, so you know the initial velocity in the y is 0, so this term is 0. You know the acceleration in the y, you know the displacement in the y. So you can figure out the time from this equation. So this is 0, multiply both sides by 2, divide by acceleration in the y, take the square root of that. That'll give you the time. Okay? Now if you forgot that the displacement in the y is negative, you would figure it out probably at this point because the acceleration in the y is negative. Now if you forgot both of those, it doesn't matter. Those effects cancel out then. Okay, so get the time from the y information and then come back to this equation to figure out the displacement in the x direction. Okay, good. So that's another two-dimensional motion problem. Okay, we've got a 50 kilogram crate pulled on a horizontal smooth surface. That means there's no friction. The pulling force is 10 newtons. I'll just call it tension. You can call it again whatever you want. 20 degrees above the horizontal. What is the magnitude of the acceleration? Okay, definitely need a free body diagram again. Normal force, weight, here's the tension, and then really this part is, I'll just call it Tx, is the tension that is accelerating us this direction, right? Tx, that's what's accelerating us this way. Okay, so I can use Newton's second law, net force, ma, and the acceleration is along this direction too. You have to supply the force. Now the only thing in the x direction is t sub x. Good, so we're trying to figure out acceleration. We know the mass, tx. Well, we can get tx. They give us t, but you'll have to figure out what tx is. So tx, from this picture, cosine of theta is the adjacent side over the hypotenuse. What if I would have picked sine? Well, then I would see that that would be ty. We don't need ty for this problem. But if I would have said, oh, maybe the sine will help me. Well, it turns out it doesn't because I'm not looking for ty. I'm looking for tx, so I'm going to need the cosine part. So then t times the cosine of theta is tx. And I could put that in here for tx. And then I can solve for the acceleration. So t cosine of theta divided by the mass. That will give you the acceleration. Okay, so you'll see some kind of Newton's second law problem where I throw in an angle. You have to break things into components. Okay, good. And finally, a ball is thrown straight up with no air resistance, the acceleration at the highest point. Well, the acceleration is down, right? Free body diagram is this. No matter where you are, the free body diagram is this. So the acceleration is down. If there were no acceleration down at the highest point, you would just stay there. Another graph of the velocity versus time might look something like this. So on the way up, if you throw the thing straight up, the ball straight up, the velocity is positive, becomes less and less positive. Here's the highest point, and on the way down, it does something like this. Now the acceleration is the slope of this. So the velocity is always changing. Now the velocity at the highest point is 0, but the acceleration is not 0. So explain, I would just, this and this, that's a good way of explaining it. Or you could, what I have in the graphs here, you could put into words. Okay, good. So I will be sending the test out to you. You'll have to get it back to me. I'll make a separate video on how to actually, the way that I usually just scan it. I use basically my Google Drive to scan the test. And I can, instead of trying to send, this is 7 pages, that would be kind of a I mean, it's doable. You could take 7 different pictures and send it to me. From my perspective, that's really hard to grade. I have to open 7 different files. So if you can send it to me as one file, one PDF, for example, that would be a lot easier. And I'll show you how to do it. It's actually really easy to do with Google Drive. Or if you've got a Apple product, there's something called Notes. I'll have to give you a link of how to do that. I don't have an Apple. I've got an Android. And if I ever scan anything, I just take pictures and it lets me add another picture and make a nice PDF. You're probably already familiar with it. Anyway, if you have any questions, send me an email and I will talk to you soon. Bye-bye.